Hello, it's Keith here, and this is lesson 71 of the platform-specific series of my 650 assembly programming tutorials. Today, we're going to be looking at music on the 800 and 5200 via interrupts. The music is playing with my ChibiTracks music player, which is a multi-platform tracking player software. Now, we're going to be looking at how we actually get the interrupts working, and we've done it in a way that works on both the Atari 800 and 5200. The technique is very slightly different, so that was the Atari 800 you heard there and saw. And now we're going to be looking at the 5200. Here we go, there's the emulator for this one. And so you can hear now it's the same player, the same song and everything playing. And it's only the memory address we put the interrupt handler, and also there's a slight difference to the start of the interrupt handler, but you can see it's working fine just here. Now, like with most systems, these systems are a 6502, so they have interrupt vectors at the very high area of the memory. An interrupt vector just means a 2-byte memory address, which is the actual address that is executed when the interrupt occurs. The VBlank interrupt is an NMI, non-maskable interrupt, on the Atari systems, so that's just something we have to bear in mind. Now, on these systems, that high memory area actually is entirely ROM on both of these systems, so we can't directly change that address and put our own interrupt handler in that position. But it's not a problem, because that ROM interrupt handler actually has a hook that we can sort of tap into and replace the rest of the firmware interrupt handler with our own, and we will do that today to handle the music. Now, on the Atari 5200, the memory address we're going to want to sort of replace is 0202, and we'll want to put the address of our interrupt handler at that address. On the Atari 800, it's slightly different. It's 0222. For some reason, it is a different address. Not quite sure why, but it is. Now, another thing that we do have to bear in mind is the sort of start work we'll have to do will vary. On the Atari 5200, the firmware interrupt handler doesn't actually push any registers for us, except for the flags, which is by default on the 6502's interrupt system. But none of the other X, Y, or A registers are pushed or popped for us, so we're going to need to back up and restore those. On the Atari 800, though, A, X, and Y are pushed for us, so our end of our interrupt handler will need to pop them off, but we're going to skip the push part of the routine. The example we're looking at today, as usual with my tutorials, will actually execute on both systems. I'm just using a different option here, Atari 5200 or 800, just depending on what I want to assemble for. And there's some conditional compilation within, as always, that switches different parts of the code as required. For example, the music player is the same, but the memory address, if my memory serves me correct, is actually different. But that's out of the scope of today's code. We are not looking at the graphics or the actual music player. Please see my ChibiTracks series for the music player, Chibi Sound Pro for the hardware specific sound driver for this system, and also a Mintile for the graphics routine that's drawing the moving icons. We're just looking at the addition of sound to those previous modules. I can't cover everything every single time. Okay, so first of all, just for a bit of a curiosity, let's actually take a look at the 5200 BIOS, and let's see what we actually see in the ROM, and then we'll understand what's happening when we gain control of the code. So here are the interrupt vectors here. So we've got the NMI vector here, which is the one we're interested in today, the reset vector, which is when the system restarts, and the interrupt request. Now, most systems, actually, it's an IRQ that occurs with VBlank, but apparently it is an NMI for this system. And so you can see we've got the address A2FC here. That is actually backwards, so it's little engine system, so we just need to swap that around. And so here is the code that is actually executed when the NMI occurs. Now, as I say, at the point here, the 6502 will have actually already backed up the flags register. It will not have backed up anything else, though. Now, we're doing a bit command here, which is a bit test. This is testing this value here, and basically this will set the flags accordingly. Now, what's happening next is we are storing the value in the accumulator to NMI res. Now, I guess that it's marked in the comments of this. I guess this resets the NMI, and in a lot of cases with these systems, it often doesn't matter what value we actually write to these memory mapped addresses, memory map ports. So probably any value in the accumulator will do that. I don't know the exact details of this hardware to that extent. I only know it from the point of view of the code I've written today. Now, we're then checking the minus and carry flags, which were set by this bit here. And so this is then going to branch out depending on the kind of interrupt that has occurred. A DLI is a display list interrupt. It's the VBlank we're interested in today. And if that VBI has not occurred, it's going to branch to this address here, which is simply a return here. Now, in the other cases, we are going to branch to our vectors as selected by this code up here. So the branch that's going to occur in our case is a jump to the address at address 0202. So a 2-byte value will be loaded from 0202 and 0203, and that will become the next executed address. And we're going to replace that with our interrupt handler in today's code. So let's take a look. So the start of our interrupt handler code is just here. So we've got a conditional assembly here, and so we're seeing which one of our systems we're compiling for. If it's the Atari 800, we're going to load in a different interrupt handler and a different destination address. Now the Atari 5200 that we just saw, it's 0202 and 0203 we want to write the address to, so we're loading the 16-bit address of interrupt handler, my rather unimaginatively titled interrupt handler, at that address. On the Atari 800 though, we are loading interrupt handler B, and we are loading that to 0222 and 0223 here. And we're going to see both of those in just a moment. Now that has defined our interrupt handler, but we haven't started interrupts. That is done by a register in the GTIA. The address is D4OE on both systems, and we need to set bit 6, which will enable the VBlank interrupt. The other one is the display list interrupt. I guess that's something to do with the display list, which is handling the screen draw. It's probably some kind of line level interrupt. It's not something I've looked at, so I can't give you any details on that. But this has now enabled our interrupts, and this means that one of those interrupt handlers will occur depending on the hardware we've assembled this for. So here is our interrupt handler for the Atari 5200, because remember I said the Atari 5200 hasn't pushed any registers for us. So we're pushing the accumulator X and Y onto the stack here, and when we're returning, we're popping those off the stack, and we're using RTI rather than RTS to return. RTI is return from interrupt, and that means that the flags are pulled off the stack because they're pushed automatically by the 6502. ChibiTracks is my music player. This uses the accumulator X and Y, but it also uses 8 entries in the 0 page, which are represented as 16-bit pairs HL, D, E, B, C, and IX. And so I've got a macro here that just backs up and restores those 8 values on the stack, because I use them in other places in my code. And if you don't know, I'm converting from Z80 code, so these are mimicking Z80 registers on the 6502. That's why they have those names. So that's all we need to do to update our music, and we have nothing else that we have to do for our interrupt handler. As I say, this is the version for the 5200, but remember I said the Atari 800 will back these up for us by itself. So the interrupt handler B here is for the Atari 800. Now actually, if we were assembling for the Atari 800 and we wanted to save some memory, we could remove these lines of code altogether. I wasn't worried about minimizing the length of the code in this example. This is just a minimal proof of concept example, so I didn't do that, but you probably should do that if you wanted to save as much memory as possible, because these lines are doing literally nothing. So there we go. So that's how we get our interrupts working. That's all we need to make our interrupts work. Now let's take a look at the ChibiTracks software. So ChibiTracks is the multi-platform player. It exists for Z80, 6502 and 68000. The player is these 3 files here. The tweener and fraction 16 are for calculating the in-between notes. ChibiTracks is the common code. These are the same for all 6502 systems. But Chibi Sound Pro is the platform-specific sound driver. So this handles the peculiarities of each system and allows ChibiTracks to pass common values, and they are then converted for the current systems. And so that's the part that handles the Atari 5200 and 800. So if you want to see more details of those, I've got tutorials on both of those. Please search for Chibi Sound Pro or ChibiTracks if you want to see. There's also a Windows-based tracker called ChibiTracker Pro, so please check that out. So that's how we actually include our actual code. We need a song 1, unimaginatively titled. There is the binary file exported from ChibiTracker. So that's the file. Now, we do have some options. ChibiTracks and Chibi Sound Pro need some memory, so we've allocated some memory here. They need about 128 bytes in total. So we're allocating it from this address here, and then we are mapping in some addresses there for the tracker's variables. So those are sort of being tagged onto the end of that memory range. We have some options. Allow relocation is an option I suggest you turn on. This allows the binary file to be exported to one intended address, but then it to be remapped to another one at playtime. Makes it much easier to work with, but if you're only working on a single system, you could turn that option off and it'd be a little bit faster. You see, internally in the binary file, there's offset addresses to the things like the list of instruments have the addresses of the instrument data, and so if the file is loaded to a different destination address, you have to recalculate those as a relative offset to the actual play address. It doesn't take much extra time, but it takes a little bit of extra time, a little bit of extra code. Allows speed changes more useful, and this allows you to change the playback speed at play time. Now, the alternative to this is you pre-multiply the speed at export time. That means you can't change the speed though, and you might want to do that. Finally, we have a special option for some systems. SMS transpose shifts the music up a single octave. Now, some systems can't play the lower notes very well. So I've now disabled that option, and you can hear that the notes don't represent accurately the tones that the song intends to play, and that's because the low notes aren't sufficiently varied on this system. And so the solution is just to shift everything up an octave. Now, that's not going to give the correct pitches, but it gives the correct feel of the song, so I would say that's generally preferable. So those are the options and the variables we need to define. How do we actually start the song? Well, very straightforward. We run Chibi Sound Pro init. That initializes the platform-specific sound driver as required. We then load in the address of our song into the song base variable within the ChibiTracks variables. We then run start song. That will start the song. Now that gets the song ready to play. We then just need in our interrupt handler to actually run the play option. So that will actually update the music as required. Now, if you had something like a title screen where nothing was really happening and you didn't need to worry about the speed consistency, you could just keep running that in a simple delay loop. However, for complex code where things are changing, you don't want the song to speed up and slow down depending on how much is on the screen. So the interrupt handler is going to be more preferable. Now, finally, just as an example, we're going to have a look at what happens when we change the song speed here. So I'm going to change the song speed to 3 here, and I will run this again. So you can hear the song is running much faster there, and if I change this to 9, you will hear it run slower. Now, why would you want to do this? Well, the most beneficial thing for me is this song was written for the 50 Hz Amstrad CPC, but on 60 Hz systems it plays a little bit too quickly, and so we can slow it down by changing the play speed, overriding it from the default of 5 to 6. Now that's one option, but another option will be maybe your game actually wants to speed up and slow down. You know, maybe you want to make the player feel more pressured when they're running out of time, speed the music up, or maybe you've got a sort of special effect where you go into water and everything slows down or something. You could change the music accordingly, but as I say, whatever you want to use it for, you can do so provided you've enabled that allow speed change. Now if we disable allow speed change, we will find the music plays far too fast, and the reason for that is that we didn't pre-multiply the speed into the binary file, so we need to enable allow speed change at playback time for the speed of the song to be correctly represented. So it just depends. Again, enabling that slows the player down a bit, makes it a little bit bigger, but you know, it's beneficial functionality to have. But if you don't need it, pre-multiply the speed and turn that off, save that memory. Anyway, that's all we've got for today. Hope you've liked what you've seen. Please like and subscribe. We're going to be coming back. I've got another. We were looking at Mintile. That's the graphics routine on this. I covered that before. I'm working on a more improved version called MaxTile, which allows more functionality. So that'll be coming later. So please stick around and check that out. Anyway, I hope what you've liked to have seen today. Go to the website, download the source code, the build scripts. As I always say, use the source code in any way you can, even if it's in a commercial project. I don't think my code's probably that amazing to allow you to do that, but I'd just like to tell you you can do so you don't have to worry, and you can just go ahead and make the best of it. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.